Now, we already know the principle of conservation of energy, but we can apply it to rotational systems as well, or systems that are partially rotational and partially linear. Let's say, for example, we've got a mass and it's attached to this rope here, but this rope is wound around a disc, like a pulley sort of thing. And so this mass is held initially 98 centimeters off the ground. The wheel has a radius of 3 centimeters, and the mass is 1.1 kilograms. Okay, and then the mass is released from rest. So it begins falling, the wheel begins unspooling, and I want to know what is its speed and what is the angular velocity. Oops, I can't write the word velocity. Of the wheel when the block hits the ground. And this problem we can solve using conservation of energy. Gravity is the only force acting in this scenario, and so our work done by non-conservative forces is 0, which is equal to a change in kinetic energy plus a change in potential energy. Except now our kinetic energy, instead of just being 1/2 mv squared, there's a 1/2 mv squared. There's also a rotational component, 1/2 I omega squared. And PE is still, change in PE is still mg delta H. Now, in this scenario, this block is moving at the same rate that the rope is uncoiling, which means that the angular velocity of the pulley is directly related to the linear velocity of the rope and therefore of the block. So we can rewrite this, and omega is B over R. This, I said, is a disk, and if you consult your chart, disk has moment of inertia of 1/2 m r squared. And so then this r actually winds up canceling out, so we don't even need to know. Well, I guess we will, since I wanted to know what the angular velocity of the wheel is. So eventually we'll need the radius of the wheel, but not initially. So 1/2 times 1/2 is 1/4. So we got a 1/2 mv squared, we got a 1/4 mv squared plus mg delta H. The only issue, this mass is the mass of the pulley, this mass is the mass of the block. I just realized I didn't give you a mass for the pulley, which you need. So let's say the mass of the pulley is, oh, I don't know, 85 grams. Alright, so we can start plugging stuff in. 1/2, and this is the mass of the block, 1.1 times its v squared plus 1/4 times 85.085 kilograms v squared plus m, which is 1.1, 9.8, and our delta H is negative 98 or centimeters, which is 0.98 meters. And punching that in, we can figure out the velocity of the block is 4.3004 meters per second. That's the speed of the block. And then the angular velocity of the wheel is just that v over the radius of the wheel, so that's 4.3004 divided by 0.03, 3 centimeters is 0.03 meters, which we can punch in to get 143.5 3, 4, 6, 8, etc. radians per second. And so this is a conservation of energy problem. Another conservation of energy problem, we can consider our inclined plane, and this one involves rolling motion. So let's say we have 4 objects of equal mass and radius rolling down an incline. And those are a hollow sphere, solid sphere, hollow cylinder, and solid cylinder. And then my question is, which has the greatest linear velocity at the bottom of the ramp? Okay, then what's going on here? Well, I should say rolling without slipping, so that our angular velocity is directly related to our linear velocity. So we're here, we're rolling down the hill, we're getting to here. Again, we have our conservation of mechanical energy. Our delta KE is 1/2 m b final squared minus 1/2 m b naught squared, b naught 0, plus 1/2 I omega squared plus mg delta h. Okay, so mass is the same for all of these, delta h is the same. Our moment of inertia is some fraction, I'll call it a, times mr squared, and this omega is v over r again, so those r's cancel out. So we've got 1/2 mv squared plus 1/2 a mv squared plus mg delta h, which has the greatest linear velocity at the bottom. So we want to solve for v. So v is minus mg delta h over 1/2 m plus 1/2 a m, square root, whatever that ratio is. So we can see that as a increases, the velocity will decrease, because as a is larger, the denominator is larger. So the greatest velocity is when a is the smallest. So we're looking at the ratios. Hollow sphere is just mr squared. Solid sphere is 2/5 mr squared. Hollow cylinder is 2/3 mr squared. Hollow sphere is 2/3 mr squared. 2/3. Hollow cylinder is just mr squared, and solid cylinder is 1/2 mr squared. So this tells us that the moment of inertia of the hollow cylinder is the largest, because it's got the 1. Next is the hollow sphere, 2/3, and then the 1/2 solid cylinder, and then solid sphere. And the greater moment of inertia is greater A, so the greatest velocity is when this moment of inertia is the smallest. So which has the greatest linear velocity at the bottom? The solid sphere. And then the solid cylinder, and the hollow sphere, and the hollow cylinder. Okay. Let's attach some numbers to this same problem. Let's say that our solid sphere has mass 2.3 kilograms and radius 5.4 centimeters, and it rolled 1.8 meters down a 28-degree incline. I want to find its linear speed. And we already did the setup in the math here. So our velocity is square root minus mg delta h over 1/2 m plus 1/2 times the ratio times m, which is square root, well actually the factor of mass cancels out all over the place, minus 9.8. Our delta h is minus 1.8 sine 28, minus because we're moving downward, and sine because of trig, over 1/2 plus 1/2 times a. What is the ratio? And that's the ratio for the solid sphere, which is 2/5. So again, we can punch that in and get a speed of 3.43956 whatever meters per second. It's just a couple of examples of how we can apply our newfound knowledge of kinetic energy and the principle of conservation of energy to do some problems that we haven't done before.